Miss Megha, the faculty in the Department of Chemistry. I am very happy to invite you all to this webinar. May I now request our HOD, Dr. Usha K.M. Madam, to take over.
Myself, Dr. Usha K.M., Head of the Department of Chemistry. I am happy to be your host. It is ironical that this pandemic situation has turned out to be a blessing in disguise, in that we get to enrich our knowledge by listening to eminent scientists from all over the world through virtual meetings and webinars. I am happy to welcome you all for today's national webinar. We are greatly honored to have our Honourable Vice-Chancellor, Professor P. Subrahmanya Yadapadithaya, to deliver the inaugural address for today's webinar. He has always been a great source of inspiration and encouragement to all our academic endeavors. He has made very rich contributions in the field of academics, research, and now to the administrative sphere in taking Mangalore University to greater heights. A warm welcome to you, sir. We have the honored presence of our University Registrar, Sri Raju Mogaveera. On behalf of the staff and students, I extend a hearty welcome to you, sir. It is our good pleasure that we have two distinguished, eminent scientists as resource persons to our webinar. One, Dr. S.M. Shivaprasad, Director, Karnataka Higher Education Academy, Dharwad, who has kindly agreed to deliver the keynote address. A warm welcome to you, sir.
Thank you.
The other resource person who will be delivering lecture on the main topic, namely Supramolecular Polymers, is Dr. Subi Jacob George, Senior Scientist, Jawaharlal Nehru Center for Advanced Research Center, Mangaluru. On behalf of all the staff and student participants, I extend a very warm welcome to you, sir. Welcome to you, sir.
Thank you, madam.
We have with us the main pivotal force for all our activities, our beloved principal, Dr. Uday Kumar, sir. Sir, I welcome you to this first ever webinar being organized by Department of Chemistry. Welcome to you, sir. I welcome all the faculty members from various institutions and student participants of this webinar. Dear participants, kindly cooperate and follow the instructions to make the webinar a grand success. Once again, I welcome you all for today's deliberations. Thank you. Over to you, Megha. Chancellor, Professor P. Subrahmanya Yadapadithaya, sir, to kindly deliver the inaugural address. Over to you, sir.
I am extremely delighted to know that the University College of our university, particularly the Department of Chemistry, has been organizing a webinar on Supramolecular Polymers. So in this context, esteemed Registrar of our university, Sri K. Raju Mogaveera, the Principal of University College, Dr. Uday Kumar MA, distinguished resource persons, Dr. S.M. Shivaprasad, Professor Subi Jacob George, the Coordinator of PG Studies in Chemistry, Dr. Lakshman K, Head of the Department of the Department of Chemistry, Dr. K. Musha, staff and students, learned participants, and dear friends. I am happy that we have two eminent scientists taking part in this webinar, especially Dr. S.M. Shivaprasad and Dr. Subi Jacob George. It's very appropriate that besides keynote address, a motivational talk also has been arranged in this webinar. I am sure our young researchers will be able to get inspired with this talk. Truly speaking, I am fish out of water as far as this subject is concerned, but I gather to know that supramolecular polymer chemistry is a highly specialized field of science. It has its applications in drug manufacturing, production of various pharmaceutical products, and it has applications even in the agricultural industry. Experts will be in a position to elaborate on it. All the same, I take pleasure in wishing the national webinar a grand success, which is organized by the Department of Chemistry of our University College, Mangalore. So all the very best to each and every one of you. Thank you very much for your time and opportunity.
Not fail in my duty in congratulating Dr. Usha AM and her team who have come forward with this proposal of organizing a national webinar on supramolecular polymers, and also for having identified very inspiring resource persons, Professor S.M. Shivaprasad and Professor Subi George.
Everything which happens in this world is science. So please understand, it is so beautiful and it is so enjoyable. Okay, so I just want to tell. But science has two dimensions. Okay, there are two dimensions in science. One dimension is unrevealing how the nature works. How nature works, what happened to the planets, how do the electrons revolve around the atom, what is the force between that molecule, this molecule, etc. And then you see what is the origin of the universe. These are all esoteric nature from which they try to find out the laws of nature. So the laws of nature are understood. And then once these laws are well defined, then you have the other form of science, which most of us do, which is basically some form to help mankind. Okay, this is more of a useful science. So what you are doing is one science which is an esoteric science which defines the laws, and the second science which use these laws to make something very useful. So these are two kinds of sciences which are there. Now, for example, you all know what is called as the Grand Unified Theory, the GUT. Okay, what they've done is, Abdul Salam, a Pakistani scientist, was very famous in identifying this. Okay, and other scientists who put the electromagnetic interaction, the weak interaction and the strong forces all together and found out one equation which could define all this, and this was called as the Grand Unified Theory. But ultimately, you know that we also want to include gravity into that. If we can understand gravity also and put all the forces under one equation, okay, we'll find what is called and theory of everything. If we find theory of everything, it is expected that we'll understand everything in nature. Okay, we don't need to go to the other levels of trying to understand with philosophy or spirituality or everything. Once we know this theory of everything, we may be able to understand everything in nature. I'm sure some of you have seen this movie called Stephen Hawking's Life movie, which is called as the theory of everything. Of course, there's not much science in it, but it's a beautiful story of trying to tell how science is pursued. Okay, how beautiful it is. Again, last year's Nobel Prizes. I'm sure you all know last year's who were the Nobel Prizes winners in chemistry. You should know. If you don't know, please do that. And again, this year you will again get some more names. So as students of chemistry, you should know every year who are the Nobel Prize winners in chemistry, also the teachers, and also you should know why they got their Nobel Prizes. Okay, these are very simple, most important things when we are doing the profession or we are a student of science. See, last year, there were two interesting prizes. One was for esoteric science. In physics, it was given for physical cosmology. Okay, people were in Kuwait got the Nobel Prize for physical cosmology. Physical cosmology means people say, why do they want to study the universe? Okay, why do they want to study the origin of the universe? Why do they want to see what was the Big Bang theory, what was real, not real? Is it a waste of time? The God particle, that whole Hadron Collider experiment which was done there. I mean, these are amazing things which are done to understand nature, to come with the laws of nature for us to understand what is nature and come out with these laws. And then, the Nobel Prize for Chemistry last year was given for lithium-ion batteries. Okay, Goodenough, Whittingham, and Yoshiro got the Nobel Prize for lithium-ion batteries. See, you see so beautifully, the physics were given for the esoteric science, and the chemistry Nobel Prize were given for something very useful. So this combination, I just want to tell you, is actually science. So we can choose what you want to do, what kind of science you want to do. You want to do esoteric science or you want to do some useful science. These are some things we need to understand. To do this, we need to understand, first of all, as students of science, we need to understand the difference between science, technology, and engineering. We all tend to think that science, technology, and engineering are the same. That's why we are confused with everywhere. I call it as Council of Scientific and Industrial Research. I call it Department of Science and Technology. I mean, we mess up. All sorts of things are messed. We don't understand. Engineering colleges, you don't know whether they're engineering colleges or technology colleges, and you don't know which is science and which is art. Like most of us tend to call Abdul Kalam as a scientist, though he's not. He's a great engineer, he's a technocrat, but he's not a scientist. So what is the difference? At least science students should know. The common man may not know what is the difference between science, engineering and technology, but as scientists we should know. Science is something which is done for curiosity. That means a scientist, a real scientist, if you ask him what he is doing to achieve what, okay, he has no idea. If he knows what he is doing, then he is not doing science. So he should not know what is science, because he is working at the edge of ignorance and knowledge. He's working on the edge trying to find out something new. Out of curiosity, he wants to find out what happens next. And that question is bothering a scientist. And that is why inventions, discoveries and inventions are made by scientists. They discover things for the first time and they invent things for the first time. This is what a science is all about. Then you have technology. Technology means they look at the scientists, what they are doing, they pick up the laws which the scientists are doing, collect them together and say, oh, I can put all of them together and make something useful. For example, they'll say, can I put all this science, what the scientists have done, and I can make a pen out of it. Okay, and that is a technologist, the bringing the concept. So that is why a technologist thinks about utility, okay, a good or bad utility, even making a nuclear bomb, for example, and then he says that he innovates things. He innovates discoveries and the inventions of the scientist. So the technologist does not invent and does not discover, but he uses those laws and tries to find out something useful, and that is called as innovation, right? And then ultimately it is the engineer. Somebody has to make this product. I mean, the technologist said that I can make a pen, but ultimately somebody has to make a pen. And that who makes this pen is an engineer, right? So you understand, and so the scientist invents, the technologist innovates, and the engineer improvises. So you need this different combination of things. So now as students of science, you have to make a decision. What kind of science I want, whether I want to become a scientist, I want to become a technologist, I want to become an engineer. It is all possible at every stage of your life. Okay, at every stage of your life, you can choose these fields. And so which psychology suits you? You need to think about it. So you have to read a little bit more about science, a little bit more about technology, a little bit more about engineering, and start thinking, where do my natures fit in? And if you look at and find the nature and find the combination where your nature is synchronized with the subject, then you will enjoy this profession. And you will go miles in this because you start enjoying your work. And once you start enjoying your work, there is no tiredness, there is no hard work. It isn't called as hard work. It will be called ishtapattu madodu, kashtapattu madodalla, right? Only it happens once you start enjoying it. So to enjoy a particular subject, you need to identify yourself. Everybody's psychology is different, every field is different. So you need to identify what excites you, what enjoys you, and that effort is what you do during education. When you're doing your graduation or post-graduation, what you are trying to do is actually trying to understand and identify what you want to do in life, what you enjoy doing in life. So that is the purpose of education. Please think about it. It is not for your degree or for your job or anything of that sort. A science education is only to identify where I will enjoy my life. Okay, whether I want to become a scientist, a technologist, or an engineer. See now, for example, let us say, look at Corona. Okay, Corona has hit the world. As Sir said very beautifully, he said that all the temples, the mosques, except one temple yesterday, unfortunately, all the temples, the mosques, and the churches have been closed. Okay, and people are depending on science, right? On science to deliver what is required. So, the mathematicians are working on models, the biologists and the biochemists are working on medicines, the doctors are working on saving children. Absolutely science is in action. But look at it. Look at our universities. Our university, Karnataka University, okay, or Mangalore University, they have closed down. When the whole science people are working, we have closed down because we have nothing to offer. You understand? We have nothing to offer because we have not prepared ourselves to that knowledge where we can offer. Why not? Mangalore University should be working on producing the vaccines or working on mathematical modeling to see how it is being spread in our state. Karnataka University should be doing that. All our universities should have been doing that. But unfortunately, we have closed down. Okay, we are closed down and sitting in our houses doing nothing. That means we are not yet geared up to take up these challenges. We are again waiting for Oxford to release the vaccine. Okay, we are waiting for somebody else to do this vaccine. We are just praying. Only what we are doing is we are putting all the fake news, photoshopped images, and showing that India is great. Okay, you saw that recently the Rafale plane came on Italy and they showed an Italian picture, it's a French Rafale. Okay, I mean, because their colors of their flag is also similar like ours. I mean, and yesterday they showed that on Times Now Square, Rama's images were put, which is all again rubbish. So we are busy doing these things. We are not doing the real science, the real part of it. And that challenge is we need to take. Of course, if you ask people who are working in science in our universities, they'll say, we don't have funding, sir, we don't have support, etc., etc. That reminds us of our great scientist, Sir C.V. Raman. His equipment costed him 160 rupees. Okay, but his brain was invaluable. So he used this invaluable brain, which all of you have, I suppose. I don't have one, but all of you have this brain. So use that. And your brain is same as C.V. Raman's brain, let me tell you. Okay, it is everybody's brain is similar, but he decided to use his brain. And he decided to spend 160 rupees on his equipment and find out what is called as the Raman Effect. He just found out that a photon, when it hits a body, just before him, Rayleigh had found out that if a photon hits a body, because the body is much heavier, there is an inelastic scattering, that the particle goes without losing any energy, right? An elastic scattering. Then Raman said, but if the molecules are moving or vibrating, the energy of the photon will become increase or decrease, which are called as the Stokes and anti-Stokes, and it will just increase and decrease. That's all the concept was. The concept was, if a body scatters, okay, how will it lose or gain energy because of the vibration? And that gave C.V. Raman the Nobel Prize. Okay. I mean, Raman is an amazingly inspiring person for us, for all Indians, because, Raman, at the age of 18, when he was 17, 18, he wrote his first research paper in his college and there was no research in his whole college. They just did an experiment. For example, his teacher took him to the laboratory and showed they had a single slit experiment where they put a beam of light and they saw the pattern of interference pattern, and this experiment was shown. So Raman asked his teacher, sir, what will happen if I put the light obliquely onto the slit? Okay, if I put light obliquely, what will happen? Teacher said, no, don't worry about that. Just put it straight and this is how you have to measure. That's all we teachers tell our own students, right? Students are also doing the same thing. They're not even interested in performing the experiments. Okay, because we are not curious. We are just going to cover the syllabus. All the teachers are busy covering the syllabus. I keep asking them, what is so obscene about the syllabus that you are trying to cover it? How do we open the syllabus should be our interest. So how do we open the syllabus to the students? So then Raman said that he put it at an angle, the light, and he went to the laboratory on his own. He bribed somebody to open the door of the laboratories when it was closed. He put the light at an angle and saw that there was an asymmetric pattern. And he wrote to many people to find out these patterns. And then he found out that nobody had done this in the world. Then he published his first research paper when he was 17 or 18 years old. It was just a curiosity. See, we all do this experiment. He was putting the light straight. The teacher told him to put the light straight. He just said, let me put it at an angle. What is the difference? See, that's all it is. It's only the curiosity which drives us. And that Raman, who just put the light obliquely, became that Sir C.V. Raman. It was only that curiosity which drove him, which stopped him from other interests of life, because that excited him so much. You all know the story of Raman. He was working in the the Auditor General's office in Calcutta, but he was interested in science because that always drove him. So he started and ultimately became the Nobel laureate, the only Nobel laureate in India in Indian science, right? So amazing person, very, very inspiring to all of us. So Raman is a great inspiration for all of us. What I want to tell students is that students think, I also thought that these great people are born. They are born great. So it is their genes, it's in their DNA, it is their great. So I can't do it. Okay, that is what the mistake I did. Okay, if somebody had told me at your age that no, if you are also capable, then today me and Subi George would have both got Nobel Prizes and come and to do in front of you. And Subi George may still get it, but I am too old for it now. But the question is, it is possible. So each of you, my friends, are capable of getting a Nobel Prize. Please, you are capable. Whether you get it or not depends on you. Now it depends on you whether you can do it or not. So very important for you to understand you are capable. I'll talk about this a little bit more later. Now see, this world has come to a very interesting stage. Okay, so now you know that whole civilization, human civilization, was defined based on the technology, right? We called it as a Stone Age. Then we call it as the Bronze Age, the Iron Age, okay, then the semiconductor age, then the plastic age, and now a lot of garbage. Whole civilization has been defined on technology. So but very interesting phase we have reached now. I think it's the greatest opportunity for you students, because there are three amazing technologies which have come together and which are going to transform this world in the future, in the coming future. The three technologies are nanotechnology, the second is biotechnology, and the third is artificial intelligence. The combination of these three is going to transform this world, which we have never seen earlier before. And this corona has given an opportunity for all the conventional studies to stop and the new studies to emerge. And this opportunity, I don't want any student to miss on. Okay, this is a great opportunity. I'll give you one example. In 2018, okay, July magazine, there's an article by Cordio and Wood. And the title of the article, Cordio is from MIT and Wood is from Cambridge University. They have written an article together using these three technologies together. They've written a paper. Let me tell you the name of the paper itself will shock you. It says the depth of death by the year 2045. By the year 2045, they predict that there will be no death because scientists will conquer death because now we understand death. Okay, now aging is seen only as a disease. And this has been possible. So they say by using genetic engineering, by using a lot of things, nanotechnology, nano aspects, as well as artificial intelligence and combinatorial techniques. Now they say, like, one of the major problems is telomeres. I'm sure some of you know about this, etc. So how do we control the growth of the telomeres, etc.? And then we can conquer death by the year 2045. That's what they say. And look at some of the countries, how amazingly they control the corona spread by using artificial intelligence. They mapped, okay, the whole cities, the crowds which were seeing, and the AI detected people who had the COVID virus. Okay, now, in India, the asymptomatic people, we are not able to detect. Only by tracing we are trying to do. We are not using the technology which are there because we are not prepared for it. Mangalore University is not prepared for it. Karnataka University is even JNCASR is not prepared for it. So we need to work together on this amazing thing which is possible. And amazing, I heard something very interesting. In China, 18% of the court cases are solved by artificial intelligence. Okay, there is no judge sitting there. And China, the computer gives the verdicts. So it takes only about 10 to 12 minutes for one court case to be solved. Imagine the court cases which are pending in India. Why are we not using these technologies? And AI in education, it's a big field itself. I can talk for about 2 hours, 3 hours, how people in the world are using artificial intelligence for education. Okay, we are still nowhere near that. So we need to think about these changes. In material science, amazing materials have come because of nanotechnology, biotechnology. Here today you will hear a little bit by Subi on the supramolecular structures which are there. Amazing understanding we have, and at the smallest level, at the bonding level, at the atomic molecular level. The understanding we have is giving us a lot. And what is happening with these three fields coming? The whole science is becoming interdisciplinary on its own. It is very difficult for me to survive in JNCASR if I don't understand a little bit of chemistry. And same thing, Subi has to start understanding a little bit of physics and a little bit of biology. Now it is becoming so interdisciplinary automatically. The silos of saying that now we are physicists, we are chemists, we are biologists is going away, is breaking up across. And students should understand this. Now, in our education system, we are still stuck with these boxes, right? So it's very important for the teachers to inspire our students to tell them, look, let's break out. Okay, let's go across. Let me go and sit in the chemistry class. Let me go and sit in the physics class, in the biology class. This kind of excitement we need to create. And the students also realize that is the future. Otherwise, again, after, like most of the university students do, which I'm seeing now, you will all only look for competitive exam to become a IAS officer or SDC, everything. You have studied so much of science and ultimately you'll start doing those useless file jobs, becoming an IAS officer or some clerk or some stupid thing like that. So important for me to tell you that you need to think about science. If you can understand the way the science is going, the way it is growing, you can get a very beautiful field to work on. Okay, so now the question comes is, what can I do? Right? So that is the question. Sir, idella helidri, but naan en madbekiga. Okay, now let me tell you, as I said, everybody is capable. When Einstein died, his brain was cut into several sizes to understand how was it different from others' brain. Okay, and also we know from the human is only a scholastic intelligence, which is less than 5% of what the brain uses for its other activities. Even to get up in the morning, to brush your teeth, to walk there, to look at your girlfriend, to look at your newspaper, look at WhatsApp, you need intelligence. And 99% of that intelligence is used for normal day life. What we call as scholastic intelligence is the academic intelligence is less than 0.5% or even less than that. So it is only that intelligence. So we are all equally intelligent. There is no doubt about that. We all have about 80 billion neurons in our brain. Everybody has neurons. So why are some people different from others? So the neurons on their own is useless, but you need the software to make the connections between neurons. And each neuron is dynamically capable of making about 10,000 connections. So it is 80 billion multiplied by 10,000 connections. So that is what it is. Now the question is, the difference between people who have achieved and people who have not achieved, I've realized only now, after not achieving anything in life, that I've realized that people can actually, if they focus the connections in one particular direction, okay, that is what we call them as achievers. People who focus in all different connections are called useless people in this world. Unfortunately, they are also equally intelligent, right? You ask a physics student, he can tell you wonderful stories about all the movies, all the superstars, okay, their life, not only about what happened to Sushant Singh, what is happening, what happened to Riya Chakravarti. I mean, we can talk so many beautiful things, okay, but we don't call them intelligent. We'll call them intelligent only when they get a gold medal in your examination. Unfortunate, but that is also intelligence. Now the question is, the students have to understand, we all have the capability, we have all the ability. Now it is important to make those neurons connect in a particular direction so that we can form these clusters of information and mature from information to intelligence, to application, to creativity. Again, I don't have time to explain to you how this happens in the brain. It is called as cognitive neurology. I'm studying it in the last couple of years to understand how brain works, how we think. And if we don't understand how we think, we will not know how to study, and the teachers will not know how to teach. So it's very important for all of us to understand a little bit of psychology. With fMRI scans, some beautiful knowledge is coming out. Please Google all these words. Enormous wealth of knowledge is available on the internet. Please look for that. And then another important thing for children at this age, your age, is because we were also once your age. Once upon a time, we were also young like you, smart like you, etc. Now all my hairs have grayed. Everything has become useless. Because I was also young like you at one stage. Two things bother this at this age. One, you think that you are not intelligent. You always think that the other child in the class who answers all the questions, who got all the marks, is more intelligent. As I told you, this is not true. Okay, you are also equally intelligent as the most intelligent as Einstein. Every boy here is as intelligent as Einstein. Every girl here is as intelligent as Marie Curie. Please understand this. This is very important for you to understand. You are capable. But ultimately, whether you will become Einstein or not, or you will become Marie Curie or not, or you will become another fellow who is drunk in the road or not, it's your choice. Okay, how you choose to live is your choice. But you have the capability of becoming that great person. Okay, please make that choice. Second thing which bothers you at that age is you think that I am not beautiful. Okay, because I'm not beautiful. This bothers us at that age. Okay, you start thinking, every girl is thinking I'm not so beautiful. That boy is looking only at that girl. He's not looking at me. The boy thinks that girl never gave me the second glance. She only saw me once. So he tries to do his haircut. He wants to change his look. I mean, this girl wants to go put up a lot of makeup. Okay, etc., because we think we are not beautiful. And it is one of the most stupidest things which goes in our head. Let me tell you why. As I told you, imagine all of our faces if they were like, somehow due to mutation, our faces look like the pig's face. Like this, pig's face. What you would have done is identified the most beautiful handi and made it as a film star. Right? A pig. Right? So please understand, all these parts are there, the eyes, these are only for some function. They are not for any beauty or anything of that. The beauty, as I told you, is only the mathematics, the golden mean, the Fibonacci numbers, etc., which define what is beautiful, the symmetry, etc. So there is nothing beautiful about a boy or a girl. Please understand. See, like for example, I met the most ugly man in this world, who is in India, whom I call as Abdul Khan. Probably most ugly, his hairstyle or mukha. I mean, he is very, very ugly. Then I also met the most ugly woman, which was Mother Teresa. She was extremely ugly. You know that she was ugly. See, when I'm saying that they were ugly, you must have got very angry with me. How can you call Abdul Kalam and Mother Teresa as ugly? That is if I meet you on the road, you will beat me up for saying this. Right? I'm able to say this because I'm virtually sitting far away, so I will not beat me. See, that is the thing. So though they may not have looked beautiful in the common man's view, they had what are called as beautiful minds. Okay, Abdul Kalam thought about the country. Mother Teresa thought about the people who are suffering. Okay, so they served and they built their beautiful minds, not their beautiful faces. So ultimately, we call them as beautiful human beings. So it's not the face, it's not the look, it is not what we think the common man thinks. The most beautiful thing is our mind, is our heart, is how we behave with people. So it is an opportunity for you to forget these two things, that you are not intelligent and that you are not beautiful. Please agree, everybody is intelligent and everybody is beautiful or ugly, whatever you want to call. We are all like this. Whatever we are, we are. But we have an opportunity to do this service, to become those beautiful minds by helping a lot of people. Okay, so another problem in India is we are not thinking modern. We are going back in our thoughts. We are trying to think that, ancient thing, everything is wonderful in the ancient days. It was all great at the ancient days. Now we are all spoiled, etc. Honestly, let me tell you, great contributions of Aryabhatta, Sushruta, Hemachandra, Bhaskara, Mahaviracharya. These are all wonderful people who made great contributions to the knowledge of this world, and the whole world learned from them. But the question is, we cannot get stuck there, right? So we cannot get stuck there. Things have moved from that time. Their contributions were great for those times, but they are not great for these times, today's times. We need to understand that. In fact, not only us, there are so many civilizations, the Indian civilization, the Chinese civilization, the Mesopotamian civilization, the Egyptian civilization, the Incas, the Mexican civilization, all the Mayan civilization, everybody contributed to knowledge. Right? At different times, at different places, regionally they contributed equally to this knowledge. And Indian contribution is one of the greatest among them. Great contributions. But taking that knowledge together, the modern sciences come. Right? You should not think that it comes from nowhere, it's an outside thing. Okay, now people say, chemicals. Okay, we want to hire. What is chemical? I wanted to tell you, what is dihydrogen monoxide? It's a chemical, right? It's water, right? So everything is a chemical. What do you mean by it is a chemical and not a chemical, right? So this ignorance common people have. But you should understand, it is not the question of whether it's chemical or non-chemical, it's whether it's a good chemical or a bad chemical. To understand that, we need to understand its molecular structure, in what it behaves, how the body reacts, etc. So like that, we need a little bit of modern thinking. We should be proud of our past, but we need to now think about the modern science. And science is not Western science. It is a universal science. It is everybody's science. Science cannot say that it is Western science, Indian science, Chinese science. Okay, nothing. Science is universal. It is, please accept it. And let us contribute to that great science. This is very important. Okay, so anyway, so what is important for us to say is that we need to understand the concepts very well. That is what is missing in our education system. We are not able to understand concepts. As a student, let me tell you honestly, I never understood concepts. I got a lot of marks passing all exams without understanding any concept. That is a disaster for our education system. Okay, recently a girl came here. Her father brought her here to my academy, and they said, my daughter has scored 100 marks in physics, 100 in chemistry, 100 in mathematics in the PUC. Okay, and she wants some advice of what to do. I said, I have never scored so many marks. Why you have brought her? Okay, I have to fall to her feet. I have never scored so many marks in my life. And then, but still, because my hair is great, they wanted to listen to me, like what to do in the career, etc. Then I asked her, I wanted to see her. So I asked her, what is your, can you define simple harmonic motion? Okay, she answered it beautifully, very fast, like loose motion. Okay, simple harmonic motion definition she did. Okay, very fast. Then I said, okay, I don't want to take her name. I said, okay, now tell me in this room, where do you see simple harmonic motion? Okay, the girl who scored 100 out of 100 in physics, chemistry, and mathematics could not answer that question. She did not know. It is not her mistake, my friends. It is not her mistake. She has done everything what her teacher told you should do perfectly. She has worked hard. She has by-hearted beautifully. She knows how to write the answer. She has solved all the problems. 20 years of question paper she has solved. Everything she has done, and she has scored 100 out of 100. Whatever she was told to do, she has done it perfectly. And that's why she could get 100 in all the marks. But the teachers never told her, look, this is related to the society, to life, to reality. Okay, so that is what, that's why you said, I mean, these are some things we need to change in our system if we really want to become those great scientists. And unless we become a great scientist, this country cannot become a great India. We will be copying, continue to copying everybody. Fine, nothing harm in copying, but at the same time, we also need to contribute to this. Just like our Aryabhatas and the Sushrutas contributed in ancient times, it is time for us to also contribute something very big. Like C.V. Raman contributed to this world. But tell me how many we can talk like this, right? We have one great C.N.R. Rao who is contributing, but where are the others? Right? Where are the others who are contributing to this knowledge, to this world? It's very important that all of you should start contributing. You should all decide that I need to contribute. I can contribute. I am capable of doing that. I am intelligent. I am smart. I am beautiful. I am everything. I am capable of doing this. This challenge you need to take. So the question of science is, one is to understand the concept. The second is to how to quantify the concept. Anything you need to learn how to quantify. Then you have to estimate, and then you have to know how to apply. And these are the different steps we need to do in anything we do. So this is what, again, I don't have time to explain what I want to, all these details are very interesting, but my suggestion is, if you want, at the end, I'll give my email ID. Please connect with us. Come to our academy. In the academy, we are making a small effort in this direction. We want everybody, all the teachers, all the students to participate with us so that we can make. So, okay, after this commercial break, okay, let me tell you finally what to do. Okay, so I just want to tell you, you are all beautiful, and don't settle to do trivial things in life. Plan, don't become trivial human beings like Shivaprasad. Become somebody important, somebody great. Okay, very important for you to take this decision in your mind today and tell, let me do this. Okay, so how do I, 1 minute, I think I have 2 more minutes. So I'll just tell you in last 2 minutes what to do every day. For the students, what to do in the routine. Let me tell you, science is about the question why. For everything, if you start asking the question why, you will do science. Okay. So what you do in the morning, you know, the safest, the calmest and the best place in the whole world is every day you get about 10 minutes, which is when you sit in the toilet. Okay. So enjoy that time. Okay. Enjoy that time and think about one why question in your mind. One question which is why in your mind, think about it in the morning. Okay, when you're in the toilet, because whenever my wife is angry, I run to the toilet. Well, that's where she cannot disturb me, and that is where I sit and think about it, think about anything. So thinking, the best place is the toilet. So there you think about a why question for the day. Okay, take that why question, write it on a piece of paper, and put it in your pocket. Okay, that question will bother you for the whole day. Okay, that question will keep bothering. A question which you don't know, any question, any simple stupid question. There are no stupid questions because you don't know. You have put the question. So put that question in your pocket. Okay, spend the whole day with that question. While you are doing other things, it will still bother you. At the end, find some 4 or 5 stupid fellows like you who also have sat in the toilet and wrote a question. You can make a gang, 4 or 5 gang. So go out, go to the market, eat some pani puri. After the corona, of course, not now. Okay, eat pani puri. And after the pani puri, each of you discuss this stupid question. You tell, this was my question. 5 minutes, discuss about it. Then your student will say, hey, that stupid fellow is not like this. It is like this. And he will give a question which you have an opportunity to tell, no, it is like this. Just discuss this for about 20 minutes before you go home. After you have had your pani puri. Pani puri is more important than this, but you have to do this after the pani puri. Without that, only pani puri will not help you. So link it with that. Okay, and then or go and have an ice cream. In Mangalore, you get some beautiful ice cream. I know that there's a beautiful shop. I went there. I forgot. Very, very wonderful ice creams are there. I'll talk about it later. Okay, so you take that question, talk about it, then go home, and then Google about that question for 20 minutes. Just that question, what you talked, and then Google about it. Google will give you millions of answers. Okay, you just glance it. You don't have to understand. Just 20 minutes, spend some time Googling that question. And at the end of the day, before you sleep, then you do all your other routines. I mean, all important things. You have to watch your movies. You have to go with your girlfriend. You have to attend classes also sometimes. Okay, I mean, all sorts of things you can do. But ultimately, at the end of the day, go and write 1 page about what you thought about that question. The question is there, and below that you write 1 page. What all happened to you? It may be very, very stupid. It may be meaningless. So now let me tell you. Okay, now last sentence is do this for 3 years. Okay, you will become a scientist. Just do it for 3 years. You will become a scientist, a great scientist, not an ordinary scientist like me. A very good scientist like Subi. Okay, so you'll become a very good scientist. Second, you do it for 5 years. I'll assure you, you will get Padma Bhushan. Okay, you will get Padma Bhushan. Do it for 10 years, you will get a Nobel Prize. If you don't get it, you come to me. I will steal it and bring it, give it to you also. Something I'll do, but I'll give the prize for you. Okay, very important. These are some beautiful things you do. So now I just want to tell you, you have to get excited about the science. That is very important. And when you get excited about science, then you also have to learn how to become serious about science. So science, the excitement of science has to be followed by a seriousness. Right? Only when you become serious, go to the molecular level, try to understand everything which is happening, and that will become beautiful. And that is what Subi will do now. He will take you to the serious part of science to show you supramolecular chemistry, one of the most beautiful organization of things. You will see that very beautifully in his talk. So with this, I thank you all for bearing me out for such a long time. And excuse me if I have hurt somebody in this. Anyway, that is my intent. My intent is to hurt you so that you get excited. The students, you become exciting. You have to challenge the status quo. You have to challenge the thing, and you have to transform the society. Thank you all. Thank you all very much. Thank you. Everybody has left, or everybody has gone away? I don't know what
No. Thank you so much for your inspirational words, Dr. Shivaprasad. Now it's open for discussion. We can have queries for 5 minutes before we start the next lecture. Am I audible?
Yeah. Everybody has become very serious now about science. They have stopped asking questions now, yeah? Okay. Now, what we can do is maybe we can continue the program at the end. Me and Subi, we both will answer the questions, yeah?
But Professor Shivaprasad, you never told me where to get this Nobel Prize. Now only you revealed the secret. So
I told you write it for 10 years, okay, and come and ask me. I will give you. If they don't give me, I will go there, steal it, and bring and give it to you. That's what I told you, yeah?
Okay. Thank you very much for the keynote address. I think all our students and participants are inspired to become good scientists, distinguished scientists. Thank you very much, Dr. Shivaprasad.
Thank you.
Now, let us move to the next lecture by Dr. Subi Jacob George. I request Dr. Lakshman, Coordinator PG Studies in Chemistry, to introduce the next speaker. Over to you, sir.
Good morning to you all. I just have listened to a very wonderful lecture by Professor Shivaprasad sir. Now, at this national webinar on supramolecular polymers, at this hour we have resource person, Professor Subi Jacob George, Supramolecular Chemistry Laboratory, New Chemistry Unit, Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore. On behalf of Department of Chemistry, University College Mangalore, I extend a very warm welcome to Professor Subi George sir.
thank you.
I'd like to introduce Professor George at the gathering. Professor Subi George is currently leading a supramolecular chemistry group at New Chemistry Unit, Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore. He obtained his PhD degree at National Institute for Interdisciplinary Science and Technology, Trivandrum, in 2004 under Professor Ajay Ghosh. He did his postdoctoral degree at Laboratory of Macromolecular and Organic Chemistry, Inaugural University of Technology during 2005 to 2008, Netherlands. He received many awards. To name a few: Saran Jayanti Fellowship from Department of Science and Technology, Government of India in 2007, and Asian Photochemistry Association Young Scientist Award in 2015, Macis Scopus Young Scientist Award in Chemistry in 2015, and many other awards. He is a member of Editorial Advisory Board of Chemistry of Materials (SCS) and Material Horizons (RSC). His current research interests focus on functional supramolecular polymers, living and non-equilibrium supramolecular polymerization, supramolecular chirality, and organic optoelectronic materials. He has published more than 130 research publications. He has an H index of 52. And once again, I welcome Professor George sir, Subi George sir, and over to you, sir. Thank you.
Thank you, Dr. Lakshman, for your kind introduction. I hope I am audible to all. Yeah. So at the outset, let me start by thanking Dr. Usha for having me here, for inviting me for this webinar, and also the entire teachers of the University College, and also the principal of the college for having me there. So also take this opportunity to thank our dear colleague, Professor Shivaprasad, for introducing me to the Mangalore, and also probably giving an advertisement to this particular materials, like what I am going to talk about is dynamic supramolecular polymers. Any disturbances there? Shivaprasad, hello? Can you hear me properly?
Yeah, no problem. It's clear. Go ahead. Subi.
Yeah. As I told, I'm like, probably it would have been nice that Professor Shivaprasad gives his talk after me, because those who are going to get demotivated after my talk, probably it would have been ideal that Professor Shivaprasad motivates everyone after my talk. What I will be doing is just taking away from the talk of Professor Shivaprasad and to take you to the science. I'm glad to know that most of the participants are chemists. So I'll be talking to you a kind of, my objective is to introduce something called a new class of materials, which is emerging probably very recently to its full potential, which is called as dynamic supramolecular polymers. Okay, considering the undergraduate and postgraduate audience, what I'll be doing is take it a little bit lighter, in the sense I'll be trying to giving a kind of peripheral idea what is this class of materials is all about, and why we are doing research on this particular material, and what are the challenges, how can we make them, and probably what are the future application of such materials and so on. Okay, basically I have a kind of small group which is called as Supramolecular Chemistry Group. I'm sure this word is familiar to all of you, or most of you, because it's there in most of the syllabuses right now. It's got added probably a few years back. So as you can see that in the title, we have two terms. One is polymers and one is supramolecular. So I'm sure all of you are familiar with both the terms, but I will take one by one just to spend a couple of minutes before we go into the supramolecular polymers. Okay, and all of you know what is a polymer, right? So we all know about small molecules, and small molecule is all about chemistry, and there's so much of importance in vaccines, antibiotics, and drug industry, and so on. But there is another class of molecules which are really big, or macromolecules, which we call as macromolecules, which is called, is a large molecule all around us. Okay, either in some of them are in synthetic materials, and some of them are in natural systems. So these kind of molecules are also very important for many functions. So, for example, if all of you know about polymers, starting from the PET bottle we are having in front of us. And there is another class of molecules called biomolecules. If you look into our cell or biological world, you can see that there are full of proteins, DNAs, and so on. So they are all. So both these kind of molecules are very big. Or in other words, is that they are macromolecules. Okay. So there's one significant difference between this kind of proteins and these polymers. One is, I'm sure most of you know about it. So a polymer molecule is always a macromolecule, but a macromolecule is not always a polymer molecule. What I mean by is, as polymer material requires a repeating unit. Okay, it's not necessary. Although these proteins have a specific sequence, it is known that they are not repeating. Okay, so in that way, although both are big molecules, very molecular weight ranging to thousands and 10,000s, but there is a clear difference in their basic structure. One of them, we have a repeating unit, and the other one is not necessary to have a repeating on it. Although in biomolecules, sequence of how sequence individual structural units are placed plays an important role, like in DNA and RNA and so on. It's very important that polymer this year is very important. Okay, this is exactly we are celebrating 100 years of micromolecular chemistry, or when the polymer came into existence. The term polymer was coined, or a micromolecule was coined by a person called Hermann Staudinger, who got Nobel Prize in 1953. So it was in. So this is unlike in organic chemistry or any other field of chemistry. Polymer chemistry has something unique in the sense, organic chemistry, we know from the day one what are we dealing with. For example, the first organic molecule is urea, and we know that it is urea structure. But when you look into the polymers, it's completely different. No one, we know that natural rubber is a polymer, and people were using it from so many years, but no one knew what is the structure of a polymer. Okay, so everyone thought that polymer is a kind of colloidal structure where all molecules are coming together and agglomerated and forming a kind of polymeric material. But then it was in like a 1920, this classical or a landmark paper proposed by this Hermann Staudinger, where he proposed that polymer is indeed a single molecule where it is connected by repeating units. So it was, as Professor Shivaprasad mentioned, always it's nice to propose, we look for crazy ideas. So when he proposed this particular idea, it was highly criticized by many, very big scientists at that time. They told, no, you are not right. Polymers are indeed just agglomerates of small molecules. So it took some time for him to really convince everyone that this is indeed the polymer structure is actually it's a repeating unit of small molecules which is connected covalently. So this is a Uber polymerization is a German. So it is the first paper which appeared in 1920, and this year many events were planned, including American Chemical Society, to celebrate this event. But unfortunately, most of them have been cancelled because of this pandemic situation. But I just wanted to alert you, this is an important year of this polymer chemistry, and this is that how important it is because it really changed the world. Right? If you look into it around us, it's everywhere is polymer, starting from your clothing to the bulletproofs to your water bottles to anywhere, it's full of polymer. And Professor Shivaprasad mentioned that it also adds to our garbage. Right? This is always the problem is polymer recyclability of the polymer or biodegradability of the polymers. These are the two terms, or very often we talk about either biodegradability or how to recycle these polymers. I don't know how many of you have noticed that any plastic material you take it, one of these numbers should be there. Okay, so this is basically called resin identification codes. And if you take, I have a Bisleri bottle here, and if I look at it, it has the number 1, which is polyethylene terephthalate. This is very important because, as I told, some of the polymers can be recyclable. Okay, so these numbers were given to really collect them, sort them, and try to recycle. So it extends. So some of you, if you are cooking, it's very important to go and see what in the microwave oven that plastics, the plates we use is mostly polystyrene. And juice bottles, most of them are this number 5, which is polypropylene. So this is very important.
Can you show on the bottle where it is written? Probably it will be. Can you hold it?
Yeah, I'm trying to find it out. It should be written.
It's okay, Subi. No problem.
Yeah. So definitely all the bottles should have this number 1 or a. So you can see that it's a kind of recycling. Okay, this is a small bottle. My eyesight is not so good. I'm getting old, Shivaprasad. So please look into it, and definitely this is a question I asked when I teach polymer chemistry students, that any polymer you take it, you should look into. For example, if you look into this V is PVC, polyvinyl chloride. So all the pipes should have this letter. Okay, so this helps in recycling. But on the other hand, why still garbages are really piling up because there's plastic waste? One of the major issues that it is not economical to recycle it, because once we have to first segregate it, you have to clean them, then only recycle. So only few things are getting recycled, and most of them are really adding as a kind of waste. And in this context, probably it is not about biodegradability biodegradability, what we need is probably kind of recircular economy. Probably we should reuse every polymer we use. So in this context, it's very important the kind of molecules we are talking about, which is supramolecular polymer. You can think about probably we can break this polymer into a monomeric structure and reassemble them or reconstruct them and use it for another purpose or use it for the same purpose. So that context also, people are now talking about, rather than biodegradability, can we completely talk about recircular economy and recycle polymers. So in that aspect also, the supramolecular polymers is going to play an important role. Okay, this is just for your information. And once again, just wanted to introduce another name in the polymer science. This is Wallace Carothers. So he's considered as a synthetic polymer science father, because he's the first person who supported Schrodinger. He was Schrodinger's student. He went to the lab and synthesized polymer. For example, this is a famous nylon, without which we cannot think about. Most of our clothes are belonging to nylon, and you can see that it is he did not get a Nobel Prize because he died at the age of 19, just at the age of 40. Okay, so this was unfortunate because he in fact committed suicide because he was frustrated with some of the scientists, as Professor Shivaprasad mentioned. We set our goals very high and probably you will get depressed. So that time we need really inspirational talks from Professor Shivaprasad and so on. Okay, he's a wonderful synthetic chemist who just within 40 years of his life, he made most of the polymers what we know today, nylon, PET. So most of these polymers were synthesized by these Carothers. You can hear me, right, everyone? Hello?
Yeah. Loud and clear, no problem.
Yeah. Because in between I see that suddenly everything is so quiet, so I cannot see you because I shared my screen. So yeah, so he died at the age of 40. He committed suicide at the age of 40.
You have not shared any slides. Have you sharing? I don't see that. I don't see the slides. What about the organizer? Can you see the slides?
No.
No,
sir.
I have not seen a single slide up to now.
I should have. Okay, can you see now?
Yes, sir.
Okay, sorry. So I'll just quickly recap. So this is the macromolecules which I told you, and so this is the Hermann Schrodinger who got the Nobel Prize for micromolecular chemistry. I'm really sorry that I could not show these slides. So this is the Uber polymerization, the first paper which came in 1920, and so these are the basic polymer, and this is the kind of letters I was showing this. Actually, these are the kind of polymeric identification code you will be seeing in your plastics. So this is polyethylene terephthalate. This is 3 is written if it is a polyvinyl chloride. Polystyrene is number 6. Polypropylene is number 5. So these are the things you would be seeing in your plastic bottles. Okay, so this is the guy called Wallace Carothers, father of synthetic polymer science. As I told, he's really the person who went back to the lab and started synthesizing polymers and nylons, polyethylene, and so on. So he's the first person within 40 years. He achieved most of the polymer synthesis in the lab, and most of the industries like Dunlop has taken it into the industry even after his death only. Okay, so you can imagine the impact of science he had in the field of polymers. Okay, so that's all I wanted to tell about polymers. And similarly, I wanted to introduce the other term, supramolecular. Although you know about it, I just take a couple of minutes to introduce this supramolecular chemistry. So all of you know that we know about molecules, but what is supramolecular is as defined by his father, who is called Jean Marie Lang. He's still alive. He's in Strasbourg. So he's told that supramolecular chemistry is the chemistry beyond the molecule. Okay, so it was a really new proposal for the people, because at that time people were aware only molecules like urea. So this is exactly a kind of proposal polymer chemists have made in 1920. So he told that in 1980s, 1977 they got Nobel Prize. 1987 they got Nobel Prize. In 1980s they proposed that we can similarly this like polymers we make with covalently attaching to them, we can make large structures by simply assembling these molecules together, okay, by very weak interactions. Like all of you know about secondary interactions, like hydrogen bonding, van der Waals interaction, and so on. So we can also make similar micromolecular structures by assembling these molecules by weak interactions. Okay, so that was again a breakthrough. So it's actually we are talking about chemistry beyond the molecule. So far everyone was talking about at a molecular level. Even polymer is a single molecule, although it's a macromolecular, it's a single molecule. But now we started talking about beyond the molecules. And if you look into nature, this is a field everyone says is highly inspired by nature. So if you look into any nature, I mean, like natural examples, like if you look into protein structures, if you look into DNA structures, or if you look into our membranes. So wherever we look into it, these are not single molecules. Can you mute your mic? Yeah, thank you. So if you look into any of these molecules, any of these materials in the biological structures or macromolecules, they are not single molecules. They are all assembled. For example, DNA is also a kind of assembly of two strands. And if you look into proteins, also there can be, it's a protein one subunits they assemble to make big structures. That only does the function in most of the biological structures. And this is a wonderful example of our membranes, which are again assembly of so many lipid molecules. Okay, so if you look into nature, everywhere it's an assembly of the molecule which performs a function and not a single molecule. So it's very clear that supramolecular chemistry is a field which is inspired by nature, and probably scientists at some point in time thought that probably to go to a materials which has properties similar to the biological structures, we should have an assembly of molecules rather than a single molecule. So that's probably the birth of the supramolecular chemistry, and so it's about going from simple molecule to complex structures. And so this is again a cell. You can see that it's again assembly of systems. So I came so much interested is not only by a curiosity, but probably this is the one way to make us, at least in, I would say, organic materials, probably this is a very nice way to make a material, because a material cannot be made by a single molecule most of the time. So we need to assemble the molecules, and that higher level organization of the molecules is very important for any material aspects. So that is another reason. So it provides a supramolecular chemistry provides a kind of bottom-up approach for assembling molecules and making materials, and ultimately using them for a function. Okay. So just wanted to introduce these three names. I'm sure the students have read about it in their syllabus. These were the three people got Nobel Prize in 1987 for inventing the field or coined the field called supramolecular chemistry. Donald Cramji, Mary Lane, and Charles Pedersen. But then that was, as I told, this is 1990s. But they did not. This is a field probably got recognition within few years of like graphene, few years of its invention. But then that was very, if you look back to their contribution, it's very simple contribution. And right now, I don't think in this time it will not receive a Nobel Prize. Only way to get is probably by stealing. But I'm saying that the contributions from just making these simple molecules. Okay, I'm sure some of you are familiar with the Claudius, Terminals, Cavitans. So these are you can see that this is not a single molecule. So you can see that it's a kind of, there's a host molecule and there's a guest molecule. Simple metal complexes kind of thing. Okay, so this is a so again you can see that it's not single molecule. It's more than one species there. So this was the simple contributions from those guys. So what they were trying to do is to go from one molecule to the higher level, and then so this particular thing is of lot of important because many catalysis or in ion exchange and so on. So this host gas. So nowadays we don't call it really as a supramolecular chemistry field, but on the other hand, what we call them as a kind of host gas chemistry. So you can see that there is a host and there is a gas molecule. So it's a kind of host gas chemistry where it is. So if you look into the molecular structure, it's still discrete. It's not kind of extended polymeric system or not. Okay, so as I told, this is the molecules, and if you look into these molecular structures, and this is the energy minimized models, you can see that they nicely fit into the cavity available. There is no space left. So that's one of the, so it's a perfect host for a gas like this metal ions. And that is very important because this particular this is the basics of supramolecular chemistry. What means is you should have a shape complementarity. Okay, so that's well known in supramolecular chemistry by a terminology called molecular recognition. Okay, so that is something called about complementarity. So the right and left hand, when you shake hand, so it has to be both right hands, otherwise it will not fit properly. So that is the way the complementarity, the group complementarity or shape complementarity is the one of the basis of the success of a supramolecular chemistry. That means the molecular recognition is the driving force for two molecules to come together. So this is one molecular recognition is one of the basics of this particular field. And all of you know Emil Fischer to explain the enzyme catalysis and so on. He also introduced the concept called lock and key concept, again, which talks about the same thing. So for a substrate to bind to the enzyme pocket, you should have the right shape. Okay, so this is what my point is. This is one of the basic principle behind the supramolecular chemistry. You should have a complementarity in terms of shape here, and in the further slides you will see that not only shape which is important, also the group complementarity is something important, which I will come to that. And one more last thing before I go to the supramolecular polymer subject. Is, you know that this table summarizes various weak interactions, secondary interactions. As I told, supramolecular chemistry deals with the non-covalent forces to bind these molecules to make large structures. And you see that, I don't know whether it is visible, but you can see that there are a large number of secondary interactions one can think about, a chemist can think about. Ion dipole, hydrogen bond, dipole, bipole, pi-pi stacking. So these are the things you can probably design a molecule which can show these kind of interactions. And but one thing to notice is energy involved in these interactions. So it is very big. So if you look into the hydrogen bond, it's for example 120 kilojoule per mole, the most stable hydrogen bonds someone knows about it. So this is a question every time I get it when I give a talk about supramolecular polymers. So how do you use such weak interactions to make stable structures? So stability of your material will be something which is going to be really affected if you deal with such weak interactions. And so something which in scientific terms we call it as a cooperativity plays a key role there, and it is all of you know about this particular story of Oliver constrained by a multitude of weak bonds. So it's just like us human beings, when we are alone, we are feeble and it's easy to break, but when we are together, we can do many wonderful things. So this is the exact, in scientific terms, we call this cooperativity. This cooperative phenomena is not just an addition 1 plus 1, but it's more than that. So if you in a molecule, if you have both hydrogen bonds and pi-pi stacking, like DNA, I don't know, all of you know about the DNA structure. If you look into the DNA structure, I mean, in most of the classes we study only hydrogen bonding exists between them. But there is another interaction very important in DNA is the pi-pi stacking interactions between the base pairs. So if you have two aromatic units coming together, it has a strong hydrogen bonding. Pi-pi stacking interactions. So the combination of hydrogen bonding and pi-pi stacking, that cooperative effect is what is driving the stability of the DNA. Okay, so you can see that I just go back. So this is all of these interactions are very weak. So when they act together, they can make even stable structures. Okay, this field, as I told, this was nowadays it's called as a host case chemistry, and everyone is in a position to nowadays it's called as non-covalent synthesis. Okay. That means like covalent synthesis of making molecules, all of you are aware. Can we predict and program the non-covalent synthesis of such weaker structures? And you can see that this is a wonderful system reported by one of the Japanese scientists. You know that this is a large number, at least 50-60 molecules have come together to form this particular cage. And this is a kind of nano cage assembled from small molecules. You can think about doing it as a kind of nano containers for doing reactions, and people found that reactivity inside this cage is quite different from outside. So wonderful things can be done from a materials aspect when you can think about assembling these molecules into a kind of large dimensions. So although the Nobel Prize was in 80s for a simple host gas complex, over the last 30 years, people have developed this field into a kind of predictive synthesis of some of these bigger structures and materials. Okay, that lies the importance of supramolecular chemistry. So basically, as I mentioned, it is now considered as a bottom-up approach to synthesize nanomaterials. In a kind of one advantage is that since these are connected by weak interactions, they will be highly ordered. Okay, so one wonderful example I wanted to show that I'm like so most of the time organic materials has to compete with inorganic materials for its efficiency. So one again from a person from Japan, from Tokyo University, someone called Takuzo Aida. He's a pioneer in the field of supramolecular polymers. So he made a wonderful nanotubes by supramolecular assemblies. So this is a big aromatic system, and you can see that this has a kind of amphiphilic design. That means it has a hydrophobic part and a hydrophilic part. And just like our surfactant molecules or like lipid molecules, they have a tendency to form bilayers and form this kind of one-dimensional structures, and then they roll into kind of tubes. And you see that these are wonderful tubes. Okay, so it's almost similar to the carbon nanotubes, but carbon nanotubes has interesting electronic properties. So if you look into this system also, it's a kind of organic semiconductor, which has a kind of P-type semiconductivity it has. So when they stack into form this kind of tubes, there's a kind of anisotropic charge transport along the system. So, and the beauty is that this is very clean, it can be purified. So people are now thinking about organic nanotubes from this kind of materials. So this is just to demonstrate, to which extent one can use supramolecular chemistry to make materials. Okay, so let's move on. So let's move on. So it's basically I took probably a long introduction. It's about a supramolecular polymer. So what is a supramolecular polymer? So as I told, we heard about polymers. It's a kind of one-dimensional long chains of monomers which is connected by covalent bonds. Think about a molecule, a very simple molecule like this. This is not a real, this is a kind of animation made by some people in graphite experts to explain how does a supramolecular polymer looks like. So think about a small molecule like this. It has a benzene ring and 3 amide groups at the periphery. And think about you put it into a kind of appropriate solvent. And you can see that these 3 hydrogen bond and there will be a bipartite interactions between the benzene rings. So then they can interact each other and you can form long chains like this, right? Wonderful. In picture, in the movie, it looks really cool. So these are the individual monomers which comes and then form one-dimensional structures. And it can form macromolecular structures like polymer chains. But what is so different between this and the classical polymer chains? Although I thought this can form stable structures like this, one advantage is something very similar to the biological polymers is these are dynamic and reversible. So what I mean is, so if you think about this particular backbone, since the interaction energy, as I told, the energy involved in hydrogen bonding at the beginning, they are weak. Okay, so at some point in time, it is very easy to break and reform. But it will not affect the one thing you should keep it in mind that it will not affect the overall stability of the backbone. What this is, these monomers can go out and come back to the polymer chain. Okay, so what we call it as they are always in a kind of equilibrium with the surroundings and with the backbone. Or in another way, we can tell you that there is a monomer exchange dynamics. There's a dynamics. Monomer is exchanging continuously from the backbone and surroundings. This is called dynamic and reversible. So as I told, the stabilities are not so great. So if you heat it to very high temperature, we can repack them as monomers. Okay, when you disassemble what you get it is a monomer, right? So this you should recollect that what I told at the beginning. So if you want to recycle a polymer, easiest way is to convert back them to monomers and reuse them. So in that perspective, probably this is one of the ways to use recycled polymers, where you make a polymer whenever you want. After the use, you recycle them, and then so this is something which is really actively pursuing in abroad to convert this molecule as kind of recyclable polymers. Okay, so there is a continuous exchange dynamics. So what is the advantage of exchange dynamics? When I tell monomers are in a continuous exchange, there is one advantage is we can think about is a self-healing. This is exactly another lesson we learned from biology. Most of the biological structures are self-healing. That means they can, if there's a damage, they can heal themselves. Think about there is a dynamic movement of these monomers in and out of this material. Can you imagine that suppose you use this polymer to make a paint and there's a crack in the paint, if you use it for a wall, if there's a crack, and probably it can be, think about this dynamic exchange of the monomers can self-heal the material. Okay, so there are wonderful demonstrations are happening, including the last 3 to 4 years, using this material for self-healing paints and so on. And I'm sure some of these materials will definitely come into the market, because right now the self-healing paints are based on catalyst-based things, but that is not completely efficient for a certain reason I can explain if you have any doubts. So how to make such systems? So that is something which it's very, it looks very simple in the animation, that you need to just design a molecule and make such one-dimensional structures. But if it was so easy, it would have been already in the market. But that unfortunately is not the case. So you can see that what you need is a kind of, earlier I talked about shape complementarity. Now I am talking about group complementarity. So you know that polyethylene terephthalate, which is this protein, it's not a single polymer, it's a copolymer. It has a polyethylene component and terephthalate component. It's something like this. So if you have to make a linear copolymer like this, we need two monomers which has a strong complementary group, so that they can, it promotes AB kind of sequence in the polymer. Okay, or if you want a homopolymer, you need a monomer. Okay, like a polystyrene if you want to make, which has only one monomer. So you need a monomer which has a strong self-complementary group. Okay, so that is something which I'm going to talk about, is a group complementarity. Not like we talk about crown ether and carcerans. It's a host case complex where shape complementarity matter. Here what you need is a kind of group complementarity. Okay, I'm going a little bit into the chemistry here. So what? So we can think about simple carboxylic acid group, which is known to form carboxylic acid dimer. All of you know that benzoic acid can form a dimer. So probably you can think about, why don't we take terephthalic acid? Both sides acids are there in the para position. Benzene 1,4 dicarboxylic acid, and then probably you can put it into water. It may form a one-dimensional chain. You are right, but then one of the major issues which people could not achieve polymeric characteristic in those systems was this particular slide, which is a kind of theoretical understanding of the structure. As Professor Shivaprasad mentioned, now every field of science is highly interdisciplinary. We need computational chemists, we need physics because one of the major problems in this supramolecular polymers is characterization. Okay, it's not like classical polymers, we cannot characterize the structure. So we need to take the help of physics. So I'm saying this, so this is highly interdisciplinary. So a lot of computational chemists and theoretical people have investigated this problem, and what they found that, so you see the degree of polymerization. All of you know, I'm sure the people who have studied polymer chemistry know what is degree of polymerization. This is the number of monomers in a polymer chain. Okay, that is, you know that polymer molecular weight is there. So this is how many monomers are there in the polymer weight, polymer structure, one polymer structure if you take it. So if you take a polyethylene terephthalate, the numbers are like probably 10 lakhs or so. So if you think about it, any materials to show a polymeric properties, you should have at least 10,000 monomers in that polymeric chain. Okay. One of the famous characteristics of a polymer is its viscosity or its mechanical properties. So at least we should have a 10,000 monomers in the polymer chain. Think about you are making a kind of supramolecular polymer like this. So what is the challenge is this x-axis is a Ka. Ka is the association constant. I talked about how strong they are binding to each other. So association constant is a measure of how strong one molecule is binding to the other. And if you the association constant is somewhere here. And if you take an acid dimer, the association constant is somewhere here, 10 to the power 2. And if you take DNA, you know the ATGC base pairs are the association constant is somewhere around 10 to the power 3. Okay? So what they found that if you want to make something like 10,000 degree of polymerization, which is roughly a polymer you make, you need a complementary group, or you need molecules which can interact with an association constant of 10 to the power 7. Okay, so you can imagine that this is at least 4 orders of magnitude higher than what nature makes. Nature has DNA structure, which is a well-known hydrogen bonded system, which an association constant of 10 to the power 3. So if you want to make a supramolecular polymer purely of hydrogen bonding, what you should have is an association constant as high as 10 to the power 7. Okay, think about what is the challenge in your hand. Okay, and this is exactly the reason probably supramolecular polymers was not already came into market or something like that, because it took a while for the supramolecular chemists. They had to go back to the organic chemists to synthesize such monomers and to come up with motifs which are good as high association constant as this. Okay, and I would not have given this talk if something people could not achieve in this 10 to the power 7. So there are molecules now which has an association constant 10 to the power 7 or even higher, so that one can give supramolecular polymer, can make supramolecular polymers. So that is basically the birth of this particular field, which happened probably a decade back or 1 or 2 decades back. So I will tell a little bit molecular structures to chemistry students. So how to make such strong, I'm talking right now about hydrogen bonding, okay? This can be done with any other interactions like host-gas interactions. So why it took so much time? I'm like, as I told, we need to make something better than nature. We need to make something better than DNA to such a strong structures. So if you look into this, is one of the, these two are very similar to the DNA based pair structures, okay? And you can see that the association constant at 10 to the power 2, 10 to the power 4. Then people realize what went wrong. Again, we need to really take the help of theoretical people to come up and say what is this. And they told that each hydrogen bond is contributing only 1.88 kilocalories for the stability of these molecules. Okay, what is, I don't know whether you would be able to see it. What is more important is a secondary interaction which is contributing like plus or minus 0.7. What I mean is, so you see that red colors are secondary interactions, secondary repulsive interactions, and the green colors are secondary attractive interactions. What I mean is, so if you have a hydrogen bonded array like this is not only talking about hydrogen bond strength, how these molecules are organized in the space. I don't want to make it complicated. What I mean is, there's a secondary electrostatic interactions can help happen between this particular atom and this particular atom and this to be this. Okay, and also you know that this is electrostatic in nature. So if you have two hydrogen bonded donors like this, there can be a repulsive interactions, and two acceptor like this, there can be a repulsive interactions. And if it is A and D, it can be a attractive interaction. So what they realize that if you want to make with a 3 hydrogen bonded system, very high association constant like 10 to the power 5, all these interactions should be attractive. See, and how to get it? Only way to get is AAA like this and DDD like this. Okay, so don't worry. So in these cases, if you look into the nature system, there is always the presence of secondary electrostatic interactions. That's why it could not go above 10 to the power 4 or 10 to the power 2. So the people have made systems like AAA structures like this, DDD. So then they can have an association constant. You can see that already a couple of orders magnitude higher than the natural systems. But again, you see that it is only 10 to the power 5. And if you go back, 10 to the power 5 is not enough to make a polymer. So we need to make even better. And one of the way to make better is probably to increase the number of hydrogen bonds. Okay. So that's exactly what people have done. People have gone to quadrupole hydrogen bond systems, and you can see that this is AADD system, and this is one of the successful uridopyrimidine system, which is AADD, which has 4 secondary interactions, attractive and 2 secondary repulsive interactions. Don't worry about these things, but what is more important thing is 10 to the power 7. So it took some time, almost 10 years for organic chemists with a focused approach. We need to increase association constant. So this is sometimes the creativity comes into picture. And all of you can imagine that if you can make a group where AAAA is there and DDDD is there, probably we can get even higher association constant. So these are some of the challenges some of you can think about and come up with, students can think about and come up with interesting designs and make them. And probably you can even make better supramolecular polymers. So as I told, each scientific problem has its own challenges. Supramolecular chemists cannot simply go and make a supramolecular polymer. You need real synthetic organic chemists behind them to really make structures like as high association constant as this. But this can be same with the hydrophobic system. So before that, so if what one should do if we synthesize something like this, very simple. We can think about you attach these molecules to a kind of linear chain, both sides this molecule, and just put it in a solvent. They will come together and form a linear polymer chain, and then which has a degree of polymerization very high. Okay, so this was one of the first challenge was to make system very high association constant. All of you know, I'm sure this slide is very popular slide. You know that this particular movie where the hero tries to kill the villain, but then it can always self-heal. Okay, so this is one of the one of the realistic application, very promising application of a material, supramolecular polymer. So as I told, this is the same moiety which I showed before, 10 to the power 7 association constant, and take some linear kind of this, put these two molecules, these groups to the both sides, and these are self-complementary groups because they can form hydrogen bond with itself like an acid dimer, and you put it in water, you can just make a wonderful polymer material. Okay, so I want to play this video. Can you see this now, or Shivaprasad, can you see this?
Yeah. You can see it. Yeah.
So this is a company which came in on something called Supramolecules. This is one of the first companies started to sell this material, and this is quite popular, made up of this particular uridopyrimidines. So you can see that you cut this material into two and then put back together, they completely self-heal, and it can hold almost the same weight as before. Okay, so this is a wonderful self-healing example of this. Okay, it's a kind of regenerating the damage. Coatings also we can think about it. So so if you make a coating out of this and you particularly make a crack and then allow it to self-heal, it will self-heal. Okay, I'm just so you can look into Supramolecular. They're not a partner in that, but I'm saying that I just took this video to just show how efficiently this kind of polymeric materials can work. So it can make me gel, and then it can self-heal. You can do multiple things with that particular structure. Okay, so we'll move on. So this is one of the wonderful applications of the supramolecular polymer. So my objective is to introduce you why supramolecular polymers. How I took only one example to just show that. How cleverly one can make such polymeric structures and can be used for various applications. Okay, and one more important thing which is really from the
Sir, sorry to interrupt. I think the slides can be made more bigger, like full screen.
Can you see it?
Yeah.
Yes, sir, thank you.
Okay, so so just to carry on, that was about the self-healing abilities of this kind of polymers. And something which is important is in biological system also, this has a wonderful molecular recognition. As I told at the beginning, only the right shape we can recognize the right molecule. But you know that the Nobel Prize contributions are just as a single molecule. People cannot really visualize it. So even if you think about making two macromolecular materials, real materials of this kind of polymers, one has this host and one has this gas, and just put it to them, you can see that they can really recognize them and self-heal. So because one surface of this material will have this kind of groups, and other surface will have the guest molecules, and they come together and form really kind of a kind of self-healing material. You can simply say that probably this is just coming together and sticking together, but then the next slide really tells you this is not the case. This is really the molecular chemistry translating at the micromolecular level. So as I told, it has to be the right shape. So it is highly selective. So if you make this host system with the different shapes and then attach to this polymeric material, so you can see that these are different hosts and different gas. Only the one particular thing is coming and attaching the other. Okay, the other one is still remaining in the solution. Similarly here, and this is a really four systems like that. Only one will find each other, the other one will find each other. So this is really the power of molecular recognition. Just something which just happens at the molecular level. You can see that it is really translating into a kind of microscopic materials level. So this is not only self-healing, this is actually really adaptive system, highly smart systems. That's what always people call supramolecular polymers are soft and smart materials. Okay, so this is something which I wanted to talk about it. So are they big? So this is nice. So one of the questions always I get is very nice and it looks good. So how stable are they? Okay, and it looks good in videos, and can we really use it for applications? So the question is, are they similar to the classical covalent polymers? Okay, it is indeed. Obviously, you have to take the right system. All of them may not behave the way you want. It has the right mechanical properties, and one of the classical things is a kind of viscosity systems. And as I told, when you cut the system and put it back, it can self-heal. So most of the from a mechanical properties point of view, they behaves all classical systems. And something a little bit more chemistry. So all of you know that when you study polymer chemistry, I know undergraduate it may not be there, at least for the masters in polymer chemistry. Any book you take it, you know that the classical polymers are synthesized by two different methods. One is a kind of step polymerization, which is every molecule get added in a kind of stepwise manner. The other one is kind of chain polymerization. That like polystyrene is made by a chain polymerization, where you have an initiation happens, propagation happens, and there's a termination, right? So it's a kind of chain growth polymerization, and this is a kind of step polymerization, like all PETs, all condensation polymers are synthesized by step polymerization. Okay, so people have found that, I'm not going to the details, similar mechanisms involved in the supramolecular polymerization also. There are two types of mechanisms involved in this kind of something, we call it as a kind of isodesmic versus cooperative self-assembly and so on. So similarly, models are existing. So I wanted to say that in all aspects, supramolecular polymers are almost similar to the classical polymers in terms of its mechanical properties and in terms of polymerization mechanisms. So now we can really define the degree of polymerization of, or what should be the molecular weight of this kind of materials and so on. So my objective was to really introduce these things to you. And this is a science review which came last year. And you can see that it can be used for many applications. They are as a biomaterial or as a mechanical properties materials or even optoelectronic materials. Okay, so what determines is the kind of monomers you select. If you want to push it to a kind of optoelectronic material, you should take a monomer which is optoelectronically active. If you want a biomaterial, it should be more deals with biological systems like peptides and so on. And if you want only the mechanically strong system, you can think about structures which has large number of hydrogen bonds so that you can make it really strong. So it's always a delicate balance between the dynamicity of the material and the strength of the material you want, and how you can really make something in a modular way. Okay. So I see that timing is really going out. How much time I can take more? 5 minutes? Is it okay, Usha madam?
Yes, sir, you can take 10 minutes.
Yeah. So this is something I want to say. So is it okay, Usha madam?
Yes, sir, you can take 10 minutes.
Yeah. So this is something I want to say. So last 5 to 10 minutes, always in a talk, I should tell we are also doing and what we are doing it. So this is purely the research we are doing it. Just a kind of overview of what we are doing it on this particular direction, what we are trying to do it. So there are so one of the biggest challenges is like if you look into the most of the biological system, they are well defined. They are monodisperse. Okay, we call it as a monodisperse, but most of the time when you make synthetic system, they're polydispersed. So one of the challenges to make all, if you say to me that I need a molecular weight of 10,000, I should be able to give you that. Okay. Another thing is to make a multi-component system. So in nature, again, if you look into this, most of them are complex structures with more than one monomers. So how to make it these kind of structures? This is some of the things we are doing in our lab. And another aspect is there's a although I say that biological structures are inspiration to most of the system, but then there is something very simple difference between the biological supramolecular polymers and synthetic supramolecular polymers. I would like to point it out. This is again a synthetic polymer. This is a kind of big aromatic system. You put it into water, you see that this comes together and form a large polymer. Okay, and since these bonds are very easy to break and form, so most of the time, this is a kind of simple energy landscape of such a polymerization process. Since they can form and break very fast, always we form them under thermodynamic conditions. What I mean is once you form this polymer, it will be very stable. It's not very easy to manipulate it. Otherwise, you can obviously you can go back to its monomeric structure by breaking them, but you cannot really. It's not really adaptive in the sense like biological structures is adaptive to something. So, in one of the major difference between them is, so this is again a nice video from a kind of, this is inside a cytoskeleton proteins. So you see that these are individual protein molecules, it's a microtubules, and they form this kind of one-dimensional polymers. You can see that both of them look very similar. But one of the major difference between the two structures are, this is under thermodynamic conditions, this is under kinetic conditions. I don't know whether in other ways, one people say that this is under equilibrium, this is always under non-equilibrium. And when these structures reach equilibrium, we are dead. We are no longer. We will be dead. So this is so equilibrium is a death situation in biological systems. Okay. So what we need is move from this kind of equilibrium structures to non-equilibrium structures. If you want to really make tomorrow, if some of the students might have interesting ideas that can we make an artificial cell. Okay, probably that should be one of the thing you should think about in the future. So cell is highly complex, and each cell has this kind of dynamic supramolecular systems. Okay, so this is the microtubules who heard about actin. So these all systems continuously adapt and reorganizes, which gives us motion, which gives us energy. You know that ATP binds to actin, it polymerizes, ATP hydrolyzes to ADP, which generates energy, but then it disassembles and so on. So there is a lot of complex phenomena happen inside this biological, inside a cell. So can we make something like that? So if you want to make it with the structures what we are having, this is just a kind of fancy idea I'm giving to the students, probably like Professor Shivaprasad told, you should every day think about it, can we make something like this? So the only way to achieve is you should move away from thermodynamic equilibrium and move to out of equilibrium structures. Okay, so that's one of the things, I'm not telling that we are going to make a cell, but what from a synthetic point of view, now our lab trying to make such out of equilibrium fibers, out of equilibrium supramolecular polymers. That's something which we are doing it. So this is indeed the way to make more and more complex materials, thinking matter. This is a nice review. If some of you can read it, it would be wonderful. So far we are working with this kind of passive materials. Okay, what we should do is think like nature, move to adaptive materials, living matter, and even some matter which can think, thinking matter. So to achieve these kind of things, we should really move away from this blue phase to this kind of red phase, okay, and moving more towards non-equilibrium process rather than dealing with processes which are at equilibrium. So equilibrium is very important to most of these material applications. Equilibrium is very nice, but if you want to think a little bit more complex systems, and if you want to mimic,
I already told this is the microtubules and actin polymerization. As you can see that they form when there is an energy over it, and that energy runs out, they automatically disassemble. That means this fiber is a kind of transient polymer. Means it has a definite lifetime. Once the energy runs out, this disassembles. So if you think about in a kind of slightly different way, where we can use this kind of transient behavior, we can think about transient material, right? Think about you are making a circuit which contains very secret information. Think about, and you reprogram the lifetime of the material. Otherwise, you have to find that particular thing and destroy yourself. Instead of that, you predefine the lifetime of a material. Okay, you say that it should be stable only for 1 day, and then it should disassemble itself. So you can think about such transient materials if you are moving away from equilibrium to out of equilibrium. That's one example. I don't think people have made that. And another thing, all of you know drug delivery very well. Okay, so you know that we have vesicular structures, containers. You load drugs inside that. You deliver to the target, and then that container has to break to release the drug. So think about you make a transient container. Okay? You incorporate drugs into it, and say that after 1 day or 2 days, it should simply burst. Certain cases, burst delivery is very important. So you can think about lifetime of a material. So that is one of the ways you can think about transient material. If you, from a material aspect, if you go from a kind of equilibrium structures to the out of equilibrium. I just wanted to give you some of the things we have done recently to demonstrate this concept during the last 1 to 2 years. Is we are trying to make kind of self-erasing inks. These are inks which we say that it is saved only for 2 hours. Okay, after that, that inks just disappear. Okay, this is because that ink is a kind of high energy state, it's an out of equilibrium state, and we have given some energy. Once that energy comes out, it will disappear. Ion transport, like the ion transport across the membranes. So these are something like a kind of synthetic materials. We are trying to extend this concept to this kind of, can we use this transient or out of equilibrium concepts rather than making a cell or something? Can we also make kind of materials like that? Okay, just wanted to give a flavor of what we are trying to do with supramolecular polymers. So we are trying to do is kind of make it well monodisperse, and also trying to move away from equilibrium to non-equilibrium structures, which are all challenges in this field. Okay, with that, I would like to really come to the conclusion, since almost like 1 hour is getting up. So what I tried to do was to introduce to this new kind of material, supramolecular polymers. I don't know how many of you heard about this before. This is an emerging material. As Professor Shivaprasad told, there are large number of this kind of new kind of materials are coming into picture. Probably this has a bright future, but obviously this is not like organic synthesis, which started 2 centuries back. This started probably 2 decades back. So the challenges are there in every aspect, obviously, but many groups are working on this, and probably you would be seeing probably in 10 years' time, and some of these materials are really in action. So the beauty is that it's adaptive, they're smart materials, they're responsive, they're reversible, and challenges is to go more towards complex materials, multi-component materials, and extract functions out of it. And one of the important functions people are really seriously thinking about is recyclable polymers out of this. That will solve the problems of plasticity. And then if you want particular monomer, you want to change its sequence and make it something, some other material, we can always think about doing that. So there are a lot of opportunities. I leave this imagination to most of you, and some of us are working on this particular interesting field, and we find it quite interesting, and I'm glad that I could introduce this particular materials to most of you. Before I stop, I really like to thank one of the lucky part being in JNCASR is we have many inspirational figures, seniors like Professor Shivaprasad, Professor Sina Rao. So it's a wonderful place to work in that way. I sincerely thank Professor Rao for setting up this wonderful unit called something called New Chemistry Unit. This is, I take 30 seconds to explain what is new chemistry. This is something similar to what Professor Shivaprasad told. Not only among different subjects of science, conventionally, if you look into most of the department, it had a department of organic chemistry, department of inorganic chemistry. So that is no longer there. It's all about chemistry is kind of, I cannot call myself as an organic chemist because I do a lot of physical chemistry to characterize these polymers. So new chemistry is not because it's a new chemistry department, it's because we are supposed to do new chemistry by working at the interdisciplinary areas. That was the vision Professor Rao had 10 years back or 12 years back. So it's wonderful to be part of such a department, and also in the middle of helping seniors. And also, this is my group, and most of the work is done with the help of them. And thank you. This is a wonderful. I don't know how many of visited JNCASR. So this is a really beautiful campus. It's a kind of shrine of science, I would say. So there's also thanks to Professor Rao for establishing a wonderful ambience so that we can do science. And some of you if you get an opportunity to come to Bangalore, please visit JNCASR as well. Thank you for your attention, and I'm very happy to answer questions if you have some questions. Yeah, thank you.
Thank you very much, sir. Am I audible?
Yeah.
Thank you very much for us. You have taken us to a new field of chemistry. It's a wonderful topic and emerging field. And sir, we are lucky. We have visited your campus. Dr. Shivaprasad. Yes, because of him we could go there. It's a beautiful campus. And we are very fortunate to have Professor Sina Rao's students here. Thank you very much, sir.
Yes,
so now we have some questions here.
Yeah, I can see them. So
yes.
I will I'll take some of them. So Sanjay Annarao has a question that future challenges and applications of supramolecular polymers. I think which I touched towards the end of the talk. So nowadays, supramolecular polymers can make it, but obviously the challenge is structural control. That means how we can control the structure. Structure not only in terms of its molecular weight, but in terms of sequence also. If you look into protein, you know that 20 amino acids and RNA, the way it synthesizes the protein structure is amazing, right? So that is something which is really a challenge for chemists to have such a sequence control. So if tomorrow you might give me 10 different monomers and ask me to make this particular sequence. Right now I don't have a way to do it. Probably maximum towards the end I should have showed this year we have gone up to 3 monomers, ABC sequence. Okay, so that's obviously one of the challenges. Structural control is a biggest challenges in this in the design concepts of supramolecular polymers. Applications of supramolecular polymers. Another thing is any material is wonderful, but obviously the scaling up of the material for an industrial application is something which is beyond our control, and obviously that is one of the challenges is going to face in the supramolecular polymers, because the Suprapolix company, that's probably the only company in the market right now selling this product, and that is only that particular polymer which is a self-healing material. So to convert from the basics to the application side and finally to the market, it takes some time. But obviously from a scientist point of view, what I want to do is to have this structural control in this particular field, both in terms of sequence and structural control. That is, I would consider that as one of the biggest challenges in the field of supramolecular polymer. Why is supramolecular chemistry so important? There's a question from Srilakshmi. Yeah, I hope, did you ask this question at the beginning of the talk or at the end of the talk? At the end of the talk. Okay, so, yeah. So as I try to explain to you why it is so important, because
Subi, I think now Srilakshmi herself can answer why it is important now. Yeah.
Yeah. So Srilakshmi, you are there?
Yeah.
Yeah, so I think, so as I told, supramolecular chemistry is something which is really triggered by a curiosity. As I told, we want to make something more complex and complex. That is a scientist's enthusiasm. That was the beginning of supramolecular chemistry. So probably it took some like 20 years to realize that it has huge potential in terms of material aspects. As I told, self-healing material. One example I take it. Self-healing material. Which is in the market has this beads which has catalyst. Okay, so when you have a crack, this crack should hit that bead and should open the bead and release the catalyst to trigger it, and there are some free monomers to self-heal. Okay, you can think about that a situation where crack cannot find the bead. Okay, and one way people try to address this by increasing the number of beads in the system, but then that will affect the mechanical properties. So you don't need such complicated design. I'm not telling that it's the solution, but I'm saying that one wonderful objective of a self-healing material would be making a self-healing paint with these materials, and then by continuous exchange. This is so. I take because Srilakshmi to come up with more and more imaginations like that. It's a wonderful field. It is dynamic. It is like adaptive, just like biological system. And I think it's our imagination which should take it to the applications. Okay, and I think it's in that way, chemistry beyond the molecule is a very important subject. We should go to more and more complex systems. Srilakshmi, if you have further debates on this, I think we can always email me. We can talk about it. Okay. Yeah. So. 1237 MK as a question, what is the difference between supramolecular polymers and normal polymers, which also try to explain structure wise very similar. Only difference is that one is driven by strong covalent bonds, other one is weak non-covalent bonds. So as a result, the supramolecular polymers is reversible and dynamic. And the second part of the question is supramolecular polymers is biodegradable. I try to again mention you don't need a biodegradability here. The reason is you have these are structures which you can even break down to monomers by heating or something. So you can convert always a supramolecular polymers back to the monomers and reuse it. So the concept of biodegradability is not something which we are looking for here to reuse the monomers. So that's a recyclability is something which we should think about, and that's the potential of supramolecular polymers. Rather than that's why everything cannot be biodegradable. That's one of the issues. Biodegradability polymers, every material cannot be biodegradable. We should have a alternative approach. That's why something to reuse it, instead of piling up the garbage, reusing them is the way forward, I believe. And and biodegradability also, it takes long time. So that way, I think supramolecular polymers has a potential. Something, if you want to note down this particular field called vitrimers, it's called vitrimers, VITRIMERS. You just Google this word vitrimers. Vitrimers are a field emerging from this supramolecular polymers. In the last 2 years, large number of science and nature paper came on this vitrimers with the objective of recyclability of this material. Okay, so you please look into that field, and I think that's the direction. And huge grants are available abroad in the vitrimers field to have a kind of recircular economy in that aspect. So so biodegradability is not something which is required. I would say that this kind of polymers, we have the recyclability comes into picture. So it's supramolecular polymers better than normal polymers. I don't say better. It depends on. There's a question from Indu. It's not about better. I mean, it depends on what application you would like to have. I don't want to probably replace this DMT with supramolecular polymer, but definitely where you need a dynamic behavior or reversibility is required, I think supramolecular polymers should be. So it depends on what kind of applications you are looking for. Obviously, there is mechanical stability, something which you should address. So there are advantages, but at the same time, I am sure that classical polymers cannot be replaced by everything by supramolecular polymers. That's for sure. Or it will take probably another 100 years of research before doing that. Is Honourable? Yeah, sure.
So there is a question by Dr. Vishalakshi. She is working on polymers.
Okay, I see that. Do these polymers have thermal stability as classical polymers for conventional fabrication process? Yeah, wonderful question. I try to address again. So thermal stability is there for these polymers for processability. So one of the beauty of this, most of these polymers are highly processable because they can be solution processed. Okay, so if you think about processability with high temperature, you can design it by the kind of that suprapolics, the material which has, it can be even processed, they are thermally stable as well. So, but some of the molecules we make it cannot be so high temperature. So because we are not looking into the mechanical aspects of using a polymer for mechanical properties. Okay, so it's possible you can fine tune the molecular structure. Again, chemists come into the picture. You have to design molecular structures what you want, and definitely people are using it under processability. You can see that self-healing paints are all, so they are processable. Only the certain class of supramolecular polymers, not everything. Okay, so that I think that clears. And because, as I told, there are challenges. Obviously, the stability. This is a question always we get it because whenever we talk about we make a material with the non-covalent interactions, people immediately say that they are not stable. As I told, the stability is not in that aspect. The stability, overall stability, thermodynamic stability is there of the polymer. What is not there is what is advantage is the kinetic stability. What I mean is the monomers goes out and come back. We call it as a kinetic stability of the system rather than the overall thermodynamic stability of the system. So that time scales are, in some cases it is extremely fast, like microseconds. Some cases it can be seconds, sometimes it's hours. So the kinetic stability can vary from seconds to the hours or milliseconds. So overall structure is stable. That doesn't mean that this monomers going out and coming in doesn't mean that overall structure is not stable. Okay, so that's a slightly different concept you should understand. So they are stable because you know that water molecules are simple hydrogen bonding, right? They're stable up to 100 degrees. So we have additional pi-pi taking interactions and so on. So there you can see that we can fine-tune the interaction energies to make it more stable. Okay, this depends on what kind of applications. Any particular question I should give priority? Usha,
Yes, sir. So now some questions for Shivaprasad, sir.
Okay, sure, please. Yeah.
Shivaprakash, he wants to ask a question.
Yeah.
Namaste.
Prakash.
That was very exciting, inspirational talk by you. I had tears of joy when you were explaining the opportunities the science throws out to youngsters. If they dream and then work hard, anything can be achieved, through science. So
Yes.
I just want to know one improbable possibility. For instance, in mythology, we hear that God used to appear in front of the person who is in tapas with deep reverence. He prays for him. God makes appearance physically in front of him. We read in mythology. Is that going to be a possibility in future?
First of all, it will become a possibility if God is real. So I doubt that it
Not
will.
God, not God. Some person to appear like that physically in front.
Yeah. I mean, of course, physically means in the sense that 5G technology, okay, can bring holographic images. Right? Once you get, which you already started, so you can actually create a holographic image of a person here, and we can appear right in front of you. So that God may not come, but Shivaprasad can come. Yeah. Okay, so it is already possible with the information technology. Yeah, it's already
Virtual 3D images.
Somebody appearing there. Yeah, this is already.
Thank you.
Okay.
Sir, one more question from our student Bharat Kumar.
Yeah. I saw his question about water evaporation. Is that Bharat?
Yes.
Bharat, can you switch your video on, Bharat?
Bharat.
Switch on your video and unmute your mic. Bharat? It's okay. Yeah. So the question, he says that why does water evaporate even when you don't reach 100 degrees? Hello, Bharat?
Yes, sir.
Eh?
Yes, sir.
And now, Ian, what are you studying?
BSc, sir.
BSc which year?
Third year, sir.
Okay, very nice. So now tell me, you have to tell me the answer now. Why will it evaporate before 100 degrees? Right? So because I'll just give you a hint that it is only a surface phenomenon. Means evaporation happens from the surface. Right? So what is different from the molecules which are on the surface and inside the water? What is the difference?
They're on tension, sir. Tension from pressure from atmosphere.
That is one thing, that is vapor pressure what you are defining. Yeah, I will come to that later, but I just wanted to ask you this question, that what is the difference between a water molecule which is inside in the middle of water and the one which is on the surface of water?
Freedom.
Yeah, very good. That is the freedom, right? So the question is, they are bonded much more weakly than the atoms which are inside. So you don't need 100 degrees centigrade. They can come out depending on the air pressure which is coming outside. Wonderful question. I hope it is convincing to you. You can think a little bit more on that. Yeah? Very nice. Okay. Okay, brother. Thank you. All the best.
Thank you, sir.
Okay.
Any more questions? We have another 5 minutes to wind up.
Come on, ask questions. There are no stupid questions. There are only stupid answers. Yeah. Anya Shri, can you switch on your video? We'd like to, if not a question, at least we want to see your smile. Yeah? Danya or Kumar Swami? Yes? Okay. Good. Any other question, Bharat?
There is a question.
I want students to ask questions.
One question from.
Yeah. Sir, question is yeah?
Yes, sir. Yes.
Yeah.
Siddharaj, Dr. Siddharaj.
Yeah. Dr. Siddharaj, question for Subi.
Sir, it was a wonderful talk. It's a new topic for me, supramolecules.
Okay.
So my question is, any role of supramolecules in prevention of corona, like supramolecules used in masks, PP kits, or even in gel like sanitizer?
It's a good question. I don't think people have looked into it. First, we have to say that whether supramolecular polymers will kill corona or kill us. But I'm saying that. So I'm saying, but obviously, I'm like, you can think about making them microporous and so on. Probably, I don't think, but any attempts are made in that direction. I'm like, I don't. as far as I know, it's not there because, but it can be used as coatings. So you can think that, but then obviously, so microstructure is something which has to be modulated. As far as I know, we do not think about it in that direction. I don't know
in the future, probably people can start thinking in that direction.
Yeah, definitely. Good. Yeah. You are also welcome to think some ideas with this. Any way this can help. Whichever way it is. Yeah.
Like if somebody asks this question, which is better than normal polymers, the idea is it is not different. It is different from these polymers. So there are different applications you can utilize. Like you were talking about transient survivals, right? So these are, you can think of applications related to those things. Sir, Siddharaj sir, what do you think? Why did this question come to you? Means, how do you think supramolecular chemistry can help with the corona in some sense? Well, where do you think you can apply? I mean, after the talk, let us see if you can pick up something. Sorry, I mean, there is not echo. Sorry? There's a lot of echo. Somebody else has to put off their mute. Other than you talk about it, I think it will not echo. Yeah, okay. So that is what that is.
Now it's fine, sir.
Yeah, now it's fine. Yeah.
Yeah, I was thinking like sir was explaining on self-healing molecules.
Yeah.
So anyway, there are so many masks which are used and through.
Yeah.
So if such type of mask or any supramolecules, like mask designed supramolecules can throw out the dust or microbes off and it can be reused.
Wonderful idea. So we can. Yeah.
Obviously,
general idea.
Yeah, I mean that could be one of the ways forward. But I'm saying that recyclability, any aspects, any applications, I think that is supramolecular polymers provides an opportunities. As I told, people are seriously thinking about this supramolecular polymers as a recyclable material. So I think wherever you see, I mean, like a suggestions from you, but I don't know, like a supramolecular polymer, exclusively from supramolecular polymer, if you want to make a mask, you have to think about other aspects like how much air can come in and come out. So these are the aspects one has to really investigate. And most of these masks, I don't think they are made up of exclusively polymeric materials because polymeric materials, obviously the air inflow and outflow has to be modulated. So that I think that is one of the bigger challenges. I think once that is achieved, probably it can be used. Yeah.
They both also have to be about 0.3 microns or less. For the droplet to be held. Okay. Good, very nice thinking, Siddharaj sir. Please like it, inspire your own mind and inspire your students. I think a lot of beautiful things will come from your college. Very nice.
I need to mention here.
Yeah.
Dr. Siddharaj sir is our innovation club.
I can understand what he's going to put on here. Very nice.
Yeah, so there are many more questions since the time is coming up. Now we can wind up.
One more last question from a student. If there is a student who wants to ask a question, priority is always for the students. Yeah. Any student who wants to ask a question? Dhanjashri, Shush Hegde, Litika. Okay, Jayashri Kapoor. Anybody wants to ask something? Yeah.
I think as long as this next time, I can see the numbers are drastically decreasing.
Yes.
Otherwise, you have to give one more inspiration.
Yeah. Okay, so we can close, I think. Yeah.
One question is there from a student.
Yeah, very nice.
Whether self-healing character of supramolecular polymer is the advantage or disadvantage when it comes to its structure and application?
Yeah, I think I still consider this as an advantage because it's a self-repairing mechanism. So any damage in the material, wherever it is, so self-repairing is a wonderful phenomenon in our body, right? That self-repairing is any material, if you think about it, if there is a damage, doesn't need to be a big crack or anything. Any structural, because structural order is also very important for many material applications. So if there is a defect or any kind of thing, I think self-healing will help to heal it. I mean, bring back to the normal function. So I think it's always an advantage when even if it is a kind of structural applications. That's my view on that. Yeah.
Yes.
I think there are no more questions. There are many questions, but students are not ready to ask.
You can actually type in our email IDs.
Yes.
They can write.
Definitely we will provide, sir. At the end, incidentally, last but not the least, I am happy to mention here that Dr. S.M. Shivaprasad happens to be the brother of my husband. So he is very particular that I should mention it here. And because of him only, we could arrange this, we could reach Dr. Shivaprasad and Professor Subi. Thank you very much. And I have to thank my husband also here. So our principal is also back here. And now I request our colleague, Dr. Sanjay Annarao, to propose vote of thanks. Over to you, sir.
Sir, unmute, sir. Unmute your mic. Sanjay, sir, unmute your mic. Yeah.
I'm hearing, sir.
Yeah. Perfect. Yeah.
Good afternoon to everyone. Honourable Vice-Chancellor, respected Registrar, resource persons of the webinar, principal, my colleagues, and dear participants. It is great pleasure to propose vote of thanks for this webinar on supramolecular polymers. We are very grateful to Honourable Vice-Chancellor, Professor P.S. Yadapadithaya for inaugural address. We express our sincere thanks to Sri K. Raju Mogaveera, Registrar, Mangalore University for greetings and best wishes. On behalf of the Department of Chemistry, we are very thankful to Professor S.M. Shivaprasad, JNCASR, Bangalore for delivering keynote address. In his motivational speech, he explained about being a good student of science. Sir explained science as the greatest field of knowledge and explained it taking few examples from science field like physics, mathematics, medicines and chemistry and various technologies such as nanotechnology, biotechnology and artificial intelligence. Further, today's resource person of webinar delivered a wonderful talk on dynamic supramolecular polymers, new field of chemistry, growth of polymers, macromolecules, structure-specific interactions of high selectivity of supramolecules, functional supramolecular polymers, importance and its applications. By Professor Subi Jacob George, JNCASR Bangalore. We are very grateful to you, sir.
Thank you.
I thank our beloved principal, Dr. Uday Kumar, MA, for his encouragement and support for our programs. I also thank Dr. K.M. Usha, Head of the Department of Chemistry, and Dr. Lakshman K., Coordinator, PC Studies in Chemistry, for planning and organizing this webinar. I acknowledge and thank Dr. Veerabhadrappa, Head of the Department of Computer Science, Dr. Kumar Swami, Department of History, Ms. Megha Nayak, Faculty Department of Chemistry, Mr. Guru Prasad, Faculty Department of Journalism, and Mr. Bharat Kumar, final year BSc student for technical support. Special thanks to Professor Renard Nazareth, Department of Chemistry and his group, St. Aloysius College, Mangalore, for software support. Finally, I thank all participants for attending in this webinar. Thanks, one and all. Have a nice day. Thank you.